RT. How about write registers? Well, really one of two places. For an ALU instruction, it comes from the RD field. MW.IR, because remember, the write-back stage comes from the MW pipeline register,
Right.
whereas the read comes from the fetch decode pipeline register.
Right.
So it's MW.IR of RD when it's an ALU instruction.
Mhm.
Now, some of the I-type instructions have an off-label use of the source register RT as a destination register. So sometimes you read MWIR of RT, this set of 5 bits, when it's an I-type instruction. Okay? So that's where the data comes. That's where the register address, so-called addresses come from. Okay? So then, here's a single N-bit register. What is this thing? It's just a master-slave D flip-flop. You remember the way a D flip-flop works? Whatever you put in at N, when the clock strikes, that's what shows up at out. So D stands for delay. And master-slave means that it's edge triggered. So there's not going to be any glitches or race conditions or any of this kind of stuff. All right? So it's a master-slave D flip-flop. Here's the inputs. Input 0, input 1, all the way down to input of N. So this is one. How wide do we need our registers to be? 64 bits. So there would be 64 D flip-flops. Okay, and that's one register.
Right.
64 D flip-flops. And look at the way they're controlled. I've got a write signal here and a clock signal here. So if write is not asserted, then what's the output here always going to be? If write is not asserted, write is not asserted, what's the output here always going to be?
It would be
False. So when will the clock strike? Never.
no.
So if write is not asserted, I don't care what the clock does. Right? If write is not asserted, I don't care about the clock.
Right.
All right? Now, if write is asserted, then what happens when the clock strikes? And the clock strikes, and it records whatever's here, and it shows up on the output. So that signal called write down there controls whether or not something gets recorded in this single 64-bit register. Does that make sense? So now, I mean, that's kind of an ugly looking diagram. By the way, this is the, I mean, we can design it with master. This is the current state, next state diagram. It's kind of stupid, but if write is 0, then this is the current state, then this is the next state. If write is asserted. If write's not asserted, I'm sorry. It's whatever it used to be. There's no change. If write is asserted, okay, then I don't care what the current state is. The next state's going to be whatever is at N. So that's an expression of what we just said in English. If write's not asserted, the output doesn't change. If write is asserted at the next state, and when's the next state? After the clock. Does that make sense? So when you talk about current state, next state, you're talking before the clock and after the clock. All right?
What about during the clock?
It's not. It doesn't mean anything. Here, let me help you. Watch. Come here. Come up here. Come here. Stand up on this book. Stand up on the book. Okay, now when I tell you, I want you to jump onto the ground. Ready? 1, 2, 3, jump. Okay, question. Where was he when he jumped? When he jumped? No, that was before. When he jumped. No, that was after he jumped. Where was he when he jumped?
Oh,
Yeah, it's not really defined. Same problem. Same problem. So we think of before the clock and after the clock. On the clock, you can't think about it. Can't think about it. It deals with in calculus the notion of an infinitesimal and a limit, right? The limit as x approaches something. Sometimes just before the limit it exists, but at the limit it doesn't. So it's sort of that idea. Okay. sort of that idea. All right? Good. So the register can be read whenever read is not asserted. In other words, read is not write. Okay? So that's easy. Now, suppose that, oops. What am I doing? Oh, watch. Now it goes the right way. All right, this is the signal, the symbol that we will use instead of that. You see it? Instead of all that nonsense, we'll simplify it and just draw it as a box. Okay, N input bits, N output bits, a write control signal, and a clock. All right? And we'll even make it further simplified by showing it down there. So N is how wide? 64 bits. Out is how wide? 65. I show here is N bits, where N is 64. And it's got a control signal called write. And we'll just abstract away the clock, because we know that there's a clock running under the covers to control all of this. We don't care about that. We know that the clock's running. So there's a signal called load, and we apply to it write. There's 64 bits in, 64 bits out. So one of those little sort of greenish boxes is a single 64-bit register. All right? Good. So now, what does a multiplexer do? Right, it's a traffic cop. 5 roads come in, only one goes through. Right? Only one goes through. All right? So, here's the truth table. Here's the control signal S. Here's the two inputs A and B. And here's the output X. Notice that when S is 0, A goes out. When S is 1, B goes out. So that's the truth table for the multiplexer. All right? If we were to make a card map of that, okay, it looks like this. And you can see that X is S not A or S and B. All right? So that's your old undergraduate digital logic course. All right? So therefore, there's the logic diagram of a 2-input MUX. All right? Now, this is the symbol that we use. So when S is 0, what do we pick? If S is 0, what do we pick? When S is 1, what do we pick? B. That's 2-input MUX, right? Well, there's nothing magic about it being 2-input. You know, we could have still 2 inputs, but N bits. Do you see it? So here's bit N minus 1, bit 1, bit 0. So how wide is the thing? It's 64 bits, right? And in this case, it's got two 64-bit signals coming in. It's got signal A, which is 64 bits, and it's got signal B, which is 64 bits, and it's got signal S, which is a single bit, 1 or 0. Well, there's nothing magic about it being a 2-input by N-bit MUX. In fact, we could make it to be K input N bit. So the idea is K by N MUX. And here's the picture. Look. So how many inputs are there? K of them. Right? So how many bits would we need up here? Log K. What if I had 32 inputs? Then how many bits would I need? Ooh, we're going somewhere, aren't we? If I had 32 inputs, and I wanted to pick one of them, how many control bits would it take? 5. Ooh, I should be getting excited right now. 32 and 5. What does this kind of sound like? Think about the general purpose register thing. Right? So how do I, there it is. So how wide is each of these lines? No. Each of these lines is 64 bits. So I've got, for example, 32 64-bit input lines. And I've got a single 5-bit line coming in here that of the available 32 64-bit quantities, it picks one and lets it go out. Does that make sense? So that's a K by N multiplexer. A K by N multiplexer. Think of it as fat lines. I've got 32 fat lines going in and one fat line coming out. So instead of single streets coming in with a traffic cop, it's multi-lane highways coming in, and I just picked these 5 lanes.